Hi class, Miss Cornacchione here. This is topic C3, the law of conservation of energy. This is a really important lesson that's fundamental to lots of future science that you're going to learn. This picture here is a Newton's cradle, so you might have known it on my desk. And this demonstrates the law of conservation of energy. We're going to talk about similar energy transformations. So as this sphere on the left is lifted up to a height, it has potential energy. And when we let it go, this energy is transformed into kinetic energy as it speeds up. And then that energy is transferred through these 5 other spheres to the other side. And the last sphere that has that transferred kinetic energy will transform that kinetic energy into gravitational potential energy as it lifts up to a new height. So in this lesson, we're going to aim towards defining and using the terms related to energy transformations and describe a variety of energy transfers and transformations and explain them using the law of conservation of energy, and use the law of conservation of energy to solve problems. So in this lesson, the first half is talking about energy transformations and the concept of the conservation of energy. And then part 2 is the law of conservation of energy, problem solving examples, and just briefly we'll talk about what is a Rube Goldberg. So an energy transformation is when energy changes from one form to another form. So if we look at some examples, when this boy lifts up this object, where the object is gaining height, so we gain gravitational potential energy. And that gravitational potential energy is now available to turn into kinetic energy if the ball is released. And we know that the kinetic energy is increasing because the speed is increasing. So when we lift up the ball and we increase h, since we know h is in the formula for gravitational potential, h is proportional to gravitational potential, we increase gravitational potential. Then letting go, that Eg is available to be transformed into Ek. And then at the bottom, what happens? What type of energy is released here? Or that kinetic energy turns into thermal energy, the ball warms up, sound energy, and elastic energy. So in grade 12, you'll learn about the calculation for the elastic energy. Let's take another example. So recall that photosynthesis is at a very basic level where plants are using sunlight to make their own food. So radiant energy from the sunlight is transformed into the chemical potential energy that's stored in the bonds of the glucose molecules, which is essentially the plant food. Let's take a look at more conceptual examples. So Newton's cradle, depending on where you're starting and ending, could be maybe one of many examples, but specifically looking at lifting this ball up and then letting it go. We've got gravitational potential turning into kinetic. A slingshot, as you wind up, as you stretch out that elastic band, we are gaining elastic potential energy, and when you let go, that elastic potential energy gets transformed into kinetic. Free fall, so skydiving, you have gravitational potential energy at the beginning because you have a high height, then as the height is decreasing, it's turned into kinetic energy, and maybe also some sound. Ocean currents. This is an example of thermal energy transforming into kinetic. We have thunder. That's an example of electrical potential energy turning into sound. You could do the same for lightning and say electrical potential energy to radiant. electrolysis, we have electrical energy that turns into kinetic. There could be a number of different answers in many of these, just depending on what you're focusing on. So in this particular example, electrolysis, we're using electricity to decompose H2O. H2O, through electrolysis, releases hydrogen gas and oxygen gas. So as those bubbles are, the bubbling, you can see the speed of the bubbles. So if that's what I'm focusing on, the energy, that electrical energy that goes in and the speed of the bubbles coming out. Campfire is another example. In this case, we've got chemical potential energy of those bonds within the molecules in the wood that are burning, and the release of combustion is thermal radiant energy. So chemical potential to thermal or chemical potential to radiant. Ironing, we've got electrical potential to thermal energy. Solar calculator, radiant energy to electrical. And now it's important for you to try to brainstorm examples of other energy transformations and record them here to organize your answers. So as part of the practice questions, I am asking you to think of new examples and record them here. So here are some ideas. There are many, many, many examples, but here are just some ideas. Skydiving, actually we already covered that one. Trampoline, elastic potential energy at the bottom of the bounce goes into gravitational potential energy at your maximum height. Fireworks, the chemical potential energy is turning into gravitational potential energy. You could also probably use fireworks for turning into kinetic energy as the fireworks are on their way up, or radiant energy, the fact that they are bright. Sun. The sun is an example of nuclear potential energy to radiant. Hydroelectric plant, that's an example of gravitational potential energy turning into electrical potential. We're gonna really look at how electrical energy is generated in different ways. So we're gonna come back to this in more detail. Toaster is when electrical potential energy is turned into thermal. Electrical potential energy is turned into sound. Thunder, elastic potential energy, is turned into sound in a guitar and a variety of other instruments. So I think you get the idea. How many more can you think of? I challenge you to think of one for every box. Okay, so moving on. The law of conservation of energy. The law of conservation of energy states that when energy is changed from one form into another, no energy is lost. This means that the total mechanical energy at one point is equal to the total mechanical energy at another point. Written mathematically, ET1 equals ET2. This is the way that you should start all conservation of energy problems. And recall that ET at any point is made up of potential energies and kinetic energies. So for now in grade 11, we have EG plus EK makes up our mechanical energy. And therefore, if you combine these two statements, EG1 plus EK1 equals EG2 plus EK2. And this is talking about the total mechanical energy at one point, at point 1, is equal to the total mechanical energy at point 2. Okay, so let's take a look at the energy transformations at a skate park using this PhET simulation. And I've included the link to this simulation in the comments below because it's an excellent resource for exploring this. Before we look at energy transformation, let's think about what we know from the previous units, especially unit 1. So once I hit play here, this skater is gonna speed up on its way down, and then it's gonna slow down on its way up. And recall that the acceleration due to gravity vector is always pointing towards the center of the earth. But while the person is on the way down, velocity is down. And when they're on their way up the ramp, velocity is up. And when the signs or the directions of the acceleration and velocity vector match, that's acceleration. So you're traveling down, speeding up. If you're traveling up, but accelerating down, this is actually a deceleration. So just recall from unit 1, that's something that we know that is going to happen when we press play. And now let's take a look at the energies. So when you enter this simulation, you're going to notice that there's a play button at the bottom. So obviously the person is not suspended up there. This is paused in a moment of time. So I've picked up the skater and placed them at the top. I can press play and watch what happens to the speed. So as we guessed, the speed is maximum at the bottom because we know she speeds up on the way down and slows down on the way up. And at the top of either side, the speed is actually 0. So that's the reason why she reaches that maximum height, because there's no longer speed. If there was speed there, they would keep going. So let's do the same thing. Place the person at the very top, but let's look at energy. So let's turn on the pie chart. Let's turn on the bar graph. So those are located on the side. You'll also, once you enter this simulation, you'll need to turn on the grid and turn on the speed if you want to see those. We could also adjust the person's mass. So when I press play, I want you to take a close look at this energy graph. So this is showing you potential energy in blue, kinetic energy, if there is any at any point, in green, and then the total energy, that's this, this yucky puke color, that's the sum of the potential energy and kinetic energy. There's also a fourth bar, thermal energy. I've turned off friction for now, so I've simplified this simulation to have no friction. So when we press play, take a look at what happens over here. When the person is at their maximum speed at the bottom, they have maximum kinetic energy and minimal potential energy. That makes sense because they have no height at the bottom. And at the top, they have maximum potential energy and no kinetic energy. That makes sense because their object is at rest at maximum height. And then anywhere in the middle, when we add up potential and kinetic, we get total. Look at this puke-colored bar. What is this? Brown-colored bar. What is happening to the height of this bar when we press play? So notice that the quantity of gravitational potential energy decreases by the same amount that the kinetic energy increases when the skater is on the way down. So total amount of energy has not changed. This total amount of energy is just staying there. And the amount was based on how high the original position was. If there's no friction, which there isn't in this simulation, this person will go on and on forever. The total energy here equals the total energy here, equals the total energy here, equals the total energy here, and it just keeps converting from one form to another, but no energy is lost. You should log into this simulation and check when you turn on friction, what happens. So there's 3 simulations that you could log into when you go to URL, and I suggest you try the friction one and see what happens to thermal energy. Okay, going back to our PowerPoint slides. So noticing that the total amount of energy through the transformations has not changed. So total mechanical energy is constant at all points within this situation. Let's analyze the 3 positions. 8 meters high, 0 meters high, 3 meters high. Notice that there is a reference level that is established. It is arbitrary. There might be a ditch down here, and then that might make more sense to decide that as 0 meters. So this arbitrary 0 meters location, it's really important. Recall with any potential energy, you have to set your reference point. So anyways, we've got 3 different positions. Let's take a look at the energy, like quantitatively look at the energy transformations. By the way, this is a famous skater, Tony Hawk, and his mass is, let's say, 75 kilograms for the purpose of this simulation. So first, let's calculate Tony's gravitational potential energy at position number 1. So at position 1, they are 8 meters high, and we know their mass is 75 kilograms. So gravitational potential energy, that's Eg equals mgh. So we check, do we have mass? Yes. Do we have G? Yes, we have 9.81. That's a constant as long as we're near Earth's surface and on Earth and not some other planet. And then H, we can read from this graph here. Now notice, just like when you're reading from a ruler, you always look to the tick mark and then you estimate in between tick marks. So that since this is written as 8 and 6 here, it looks like it's exactly 8. So I'm going to write that as 8.0, 2 significant figures. I just substitute into my MGH, and I get this on my calculator. I notice there's 2 significant figures in the numbers, in all the numbers that I've used. Oh, this should be 9.81. And we round that to 5.9 kilojoules. So it's not wrong to use 9.8, but that chops it off as 2 significant figures. And just in case both of these other numbers were 3 significant figures, then I would also accept if you did that, but then you'd have to round, if this was 75.0 and 8.00, 3 significant figures here and here. If you used 9.81, the correct answer for full marks would be 5.89 kilojoules. If you used 2 significant figures here, which you might just look to the 2 numbers in the original problem and round to 5.9. But if this was 75 and this was 8.0 and this was 9.81, or sorry, if this was 75.0 and this was 8.00 and this was 9.8, the smallest number of sig figs is 9.8, so you would have to round to 5.9 kilojoules. So I would let you use 9.8 or 9.81, you just have to be more aware of the number of significant figures if you use the smaller number here. If you use 9.81, that's what I recommend, because the chances that 3 significant figures is the limiting number, the smallest number is smaller. So I recommend using 9.81. What about Tony's kinetic energy at position 2? So recall that kinetic energy is 1/2 mv squared. Do we have mass? Yes. Do we have v? No. We don't know speed at the bottom. We do know that it's the maximum speed, but we don't know it. So I want you to pause this video right now and see if you can think of how can you find the kinetic energy if you don't have speed. Well, this is the conservation of energy lesson, so maybe we're going to use the law of conservation of energy to solve it. So we don't know speed, but we do know that kinetic energy at the bottom is the only energy since we set H equal to 0. This makes up the total energy. So what we're really being asked here is, what is his total energy here? We already calculated his total energy up here, and they're equal. So our answer is just the previous number we got, 5.9 kilojoules. So we always start our problems with ET1 equals ET2, and then we're hopefully going to be able to simplify. In this case, at the total energy at the top was only made up of Eg, and we calculated that. And to find EK2, that happens to be all that makes up the total energy at the bottom. So that's why that is true. What's Tony's total kinetic energy? What is Tony's energy and speed at number 3? I believe I've just, so the total energy is the exact same number, 5886 joules that we calculated before, because once again, the total energy at any point in energy transformations is constant. But for speed, we're going to have to do a bit more work. So we know total energy at 3, and we know that is made up of mgh plus 1/2 mv squared. We can rearrange this for V3. So I want you to pause this video and see if you can do this rearrangement. I'm just highlighting that it's squared because students, teachers, we all tend to forget that when we're writing it out. So you should get this expression. We can substitute in all the values. We have all the values, we substitute them in, and we get a speed at the bottom, a speed of 7.3 meters per second. So these units should be meters per second. Okay. So just to reiterate, Tony's total mechanical energy at all points is constant, and it's the constant 5.9 kilojoules. Okay, moving on to another example. An incandescent light bulb is a transformation example. It's electrical energy at the beginning, and it turns into radiant energy, which is useful, which is light, and waste energy, which is thermal energy out. So let's say if we had a 100-watt light bulb, that means in 1 second, 100 joules of energy goes into this process. How much do you think turns into radiant energy? It's only, oh dear, this is supposed to disappear and say 5 joules. So only 5 joules out of the original 100 turns into light energy. 95 joules turns into waste. So because we used a nice number, 100 joules, we can look at out of 100% of the energy in, 5% was useful and 95% was waste. That's a really low efficiency. So that's one of the reasons why we've replaced incandescent light bulbs with more energy efficient options like LEDs or CFLs. Okay, so here are the steps that you should follow when you're solving any of these conservation of energy problems. So drawing a diagram is really important, and then labeling the positions that you're comparing. So maybe with numbers or letters, 1, 2, 3, ABC. Label your reference levels, so that's where H equals 0. Then write your conservation of energy statement, ET1 equals ET2. Rewrite the total mechanical energy of the system at each point as the sum of EK and EG. So that means ET1 equals ET2. The next line will be EG1 plus EK1 equals EG2 plus EK2. Simplify. Hopefully, if we were smart and we chose a reference, H equals 0, to be either at position 1 or position 2, then we'll definitely at least have something simplifying. Hopefully more than that, but if not, we can rearrange and solve. It's still solvable if nothing simplifies, as long as you're given enough givens. Then we rearrange for the unknown and plug in the numbers and solve. Make sure to conclude based on your reference level. So let's do some examples to show what that looks like. So a 70-gram egg is dropped from the top of a 2-story building, and that is a height of 6 meters. What will be its speed when it hits the ground? So if we take a look at a 70-gram egg being dropped, so we're going to label our givens in this diagram. We're going to draw a diagram, label the givens. We're going to set our reference level of H equals 0, and then draw our law of conservation of energy statement. ET1 equals ET2, and the total mechanical energy at 1 is made up of EG plus EK. Total mechanical energy at 2 is EG plus EK. Substitute in mgh for the EGs and 1/2 mv squared for the EKs. It is important to keep track of your subscripts. It's a little bit tedious, but it is really worthwhile so that you can keep track of what you're solving for. At the top is 1 point of interest. That's because we have a lot of information there. And at the bottom, that's where we're asked for information. So that's why I selected 1 and 2 to be where they are. So in this example, it's probably obvious, but we're going to move on to what I call roller coaster problems, and it might not be as obvious where to compare. So at the top, we are just releasing the egg. So it says dropped. That means V1 is 0. So this whole term cancels to 0. And the total mechanical energy at the beginning is just MGH, MGH1. Then if we look at the bottom, because we wisely set the bottom of the street to BH equals 0, strategically, MGH2 goes to 0, is 0. So we have MGH1 equals 1/2 MB2 squared. Don't forget the squared. Then at this point, we can check off what we have and what we need. And notice that mass can be factored out of both sides and canceled out. So that's convenient. We do have 70 grams, so we could just sub it in on both sides, but I'm not going to sub in what I don't need to. So that means the solution to this problem doesn't depend on mass, which is kind of awesome, that any object that is dropped from a 2-story building would have the same speed at the bottom. This is making the big assumption that there's no wasted energy. So there's not significant air resistance. So rearranging, isolating V2, we get V2 equals the square root of 2GH1. And we substitute in G and H. That means the only thing that determines the speed at the bottom of the 2-story building, the only thing that we could have really changed was the launch height. So if it was launched off of a 3-story building, it would have a higher speed at the bottom, which makes sense. We round to 2 significant figures because 6.0 was a number we used. Notice we didn't even use 70.0 grams, so we don't even consider that. And that is the answer. We actually have already done this problem using kinematics. So I want you to pause this video and see if you can solve this question using one of the 5 kinematic equations. And it turns out you'll get the square root of 2 times A times delta D. And so the more we go into challenging problems in this course, the more you'll realize that you can solve problems in different ways. So once we get to our final assessment, you'll have choices and just pick the method that you prefer. Okay, let's do another problem. So I've been talking about the roller coaster problem, so maybe now you'll know what I mean. There's a lot of law of conservation of energy problems that have to do with a roller coaster. So first, just read the problem. Many roller coasters have loops where carts roll on a track that carve sharply up into the air. At the top, the people are upside down and usually screaming. For safety reasons, many of these roller coasters must have a minimum speed at the top of the loop. So this cart here, we have height, it's going to turn into speed. Then we're going to have some height here, but also some speed is going to have to be maintained for them to make it all the way around to the end. One of my students this year was telling me that if you watch the Simpsons movie, this exact physics problem is in one form or another covered. So if you're looking for maybe a movie to watch while at home right now, maybe that one would give you some idea of this problem. So specifically, putting some numbers and actually practicing this, a frictionless roller coaster must have a minimum speed of 10 meters per second at the top of the first loop to make it around safely. So at this point here, we must have 10 meters per second speed, otherwise we don't make it around. Assuming that the roller coaster starts from rest at the top of the first hill, what is the minimum height of the first hill? So let's draw our diagram as a first step. So noticing frictionless, this just means that there's no energy lost. So it's an assumption maybe because there are wheels, maybe friction is almost negligible here. We label that we have a height that we start off, and why don't we say it's the height above the ground? Now, this is actually not maybe the smartest option for simplifying. Another option is to say the height is 0.2, but that's another way to solve the problem. This way is perfectly, you can get a perfect answer this way. You just have to be careful with rearranging your equation. So if height is at the ground level, at the top of this loop, you have 16 meters high, and the height is actually what we're trying to solve for at 0.1. So I would say, draw your diagram. Say what's 0.1 and what's 0.2. Do you have the speed and the height at each point? So we have the speed at 0.1, we don't have the height. We have the speed at 0.2, we do have the height. So we have speed and height at 0.2, which is good. That means we can calculate the total mechanical energy at that point, and that total mechanical energy there is equal to total mechanical energy at 0.1. So that's what this diagram and doodle is communicating. So we always start with the law of conservation of energy, ET1 equals ET2. Substitute in what is the definition of mechanical energy, EG1 plus EK1 equals EG2 plus EK2. Substitute in what we know is EG and what we know is EK. Then we can simplify because, oh dear. Okay, we can simplify because it says, assuming the roller coaster starts from rest, V1 is 0, the whole term goes to 0. We are solving for H1 and everything else is given, so we can move forward. You might actually notice that mass cancels out because it can be factored out of both sides. It's in all terms. If you don't notice that now, there's still an opportunity to notice it later, but we are not given the mass of the roller coaster, so it must cancel out at some point. So isolating for H1, we get mgh2 plus 1/2 mv2 squared all over mg. Now you can see mass can be factored out and crossed out on the top and the bottom. So you can reduce factors. It's factored out of the top and it's a factor on the bottom. Substitute in the numbers and you get 21 meters. That's two significant figures, which we were given 16 meters high. So 16 is two significant figures, which is why we're going to round to two significant figures. So it was really important that we drew a diagram, set a reference, and that we are really organized with the speed and height at each point. Okay, so you might be wondering, what is this cluttered picture of? So this is actually a Rube Goldberg. And if you've never seen one before or heard it described, it performs a simple task in an overly complicated way. And it's a series of steps where the action of one step triggers the beginning of the next step. And each of these steps is an energy transformation. So where an energy, one energy type turns into another energy type. For example, EG into EK. Or each step could be an energy transfer. So it could be a combination of transfers and transformations. So what I'd like you to do at the end of this video to check your understanding is watch. This is my favorite Rube Goldberg. It is actually an official music video by the band OK Go. And they've got really catchy music with videos that are often really interesting to watch because there's very little editing and they often make use of math or science. The rumor with this Rube Goldberg is that it was done all in one take. So they didn't get one success in step 1 and then success in step 2 and edit it together. They did it all in one shot, and there's a live audience that they show at the end of this video to prove it. You can see that there was a paint mess everywhere. So obviously it took them a long time, or it took them at least some trials to figure out how it would work, but they did get it all in one shot. So to check your understanding, I want you to watch this video and I want you to try and list as many energy transformations and transfers as possible. So the music video is called This Too Shall Pass by OK Go. And after that, there are some practice questions. So these 5 practice questions from the textbook, please do them and check your textbook answers with the text solutions posted on as a PDF on the Google Drive. And also fill out that worksheet where there is a table of energy transformations. So see how many, I challenge you to fill out every box. There's also this simulation and other extra resources that I highly suggest that you explore because this is a really fundamental concept in physics, the conservation of energy. Have a great day. Stay safe. Be well.